All right, so we resume our session with Markus Kirschmer. Markus will talk about algorithms for Hermitian lattices. He comes from Universität Paderborn in Germany. Markus, the floor is yours.
Thanks for the introduction. Okay, so I'll talk about algorithms for Hermitian lattices. Thanks again for the invitation. Well, before we start on the algorithms for Hermitian lattice, I want to give some short motivation what this has to do with the previous talk. Well, suppose that C is an ordinary elliptic curve over a finite field, and let R be the endomorphism ring of that curve. Now we can look at the isogeny class of G copies of C, and then there's a result by Serre, which says that the varieties in the set W, there's a bijection or an equivalence of categories between definite Hermitian lattices over R that have rank G, and it's given by this functor. Now, Serre only proves it for that case that R is the maximal order, but let's not be picky here. And recently, Christoph Ritzenthaler, Fabien Narbonne, and Damien Robert, we gave a similar equivalence of categories between the principally polarized abelian varieties, isogenous to C to the G, and the positive definite unimodular Hermitian R lattices of rank G. I'll explain in a second what that means. But this equivalence then allows us to construct or give an algorithm to construct the isomorphism classes of principal polarized abelian varieties isogenous to C to the G. In this talk, unfortunately, I didn't want to say anything more about that. So if you want to know more about the algorithm and this result, then I guess one of the three experts on varieties will know more. But that should only be well, kind of motivation of why we want to actually look at positive definite unimodular Hermitian lattices, whatever these objects are. So that's a kind of a motivation why I want to do that today. Now, for the talk, we have a certain setup. First of all, we have to introduce Hermitian spaces, and then we can talk about these Hermitian lattices. We start during the whole talk. K is an algebraic number field. Later, if you want to look at this application here, then K is just a field of rational numbers. Yeah? But it will work over any algebraic number field. And I need a quadratic étale algebra, so that's Kx modulo some polynomial of degree 2, so x squared minus dz, and bar is the canonical evolution with fixed field K. Now, a Hermitian space is simply a finite dimensional vector space over E, together with a sesquilinear map, and I want my sesquilinear map to be linear in the first component, and swapping the arguments amounts of applying the map bar. Now, we don't need all of these Hermitian spaces. In general, we will only have to deal with so-called definite spaces. And definite spaces, well, that means that K is totally real. So for us, K equals Q. And after rescaling the form by some suitable constant, we may assume that the image or the length of any vector that is non-zero is positive. Positive then means positive at all embeddings, because if the field is totally real, all the embeddings into the complex numbers are actually real embeddings, and then it makes sense to talk about positive embeddings, so positive numbers. Again, most of the time, I will only deal with these definite spaces, but some results actually work for all cases. Now, how does such a Hermitian space look like? First of all, I want my space to be non-degenerate. Well, that means more or less that if I choose an orthogonal basis by the Gram-Schmidt process, just like you learn in linear algebra, if you choose an orthogonal basis, then the diagonal entries, so the length of these basis vectors are non-zero. And then the inner product of, say, two such sums of two such linear combinations is then just the sum of, well, the coefficients xi times yi bar times the length of the ith vector. So you might actually think about a form like that, because, well, up to isometry, so up to a choice of a basis, all the forms look like that. Now, there are certain invariants associated to such a form, and the first invariant is the determinant. So that's just the product of the AI. That's, of course, I mean, a non-zero element in K, and it's only well defined up to norms, simply because I can rescale B1 by some constant, and then this would change the AI by the norm of the constant. Yeah, so of course, it's only well defined up to the norm. Now, we say that two of these Hermitian spaces, V and V prime, are isometric if there's a linear map, an E-linear map from V to V prime that respects the forms, which means that the inner product of X and Y is the inner product of the images for all possible X and Y. And then such a map phi is called an isometry. And we will need the unitary group, which is just all the isometries from phi to itself. Now, the nice thing about Hermitian spaces is that they satisfy the Hasse principle, so a local global principle, which means that suppose P is a place of K, K sub P will denote the completion of K at P. Then we can look at the completion of E at P, so that's just the extension of scalars of E with Kp. And of course, we can extend V by the scalars with Kp, so we'll get the completion of V at P. And now, again, by extension of scalars, phi extends to a sesquilinear map on Vp. And this will yield me a Hermitian space over the completion EP. And now the Hasse principle, actually for Hermitian spaces, it's due to Landher, and it states that two Hermitian spaces over E are isometric if and only if they are isometric over every completion of K. Now, of course, for a second you might think, well, that's a stupid idea to replace one space by infinitely many. But the thing is, as we already know from linear algebra, say if E is the complex numbers and K is the real numbers, then such a Hermitian space over the complex numbers, well, they are well known. They are completely described by the so-called signature. You have a Graham matrix, you diagonalize it, so you get a diagonal matrix, and the entries on the diagonal are real numbers, and then you count the number of positive and negative elements, and that's the signature. And this is a unique invariant for the isometry class over the complex numbers. And the same holds true for the completion of K and E at a finite place. They're also very easy to discover, or easy to work out invariants. And using these invariants, we come up with a complete classification of the Hermitian spaces over K, or over E, whatever you like. Namely, the first invariant is the rank. So that's the dimension of V over E. Then the signature of all the real places, where the completion of E at that place is the complex field, just like in linear algebra. And then at the finite places of K, either you tell me what the determinant is, or you tell me all the places where the determinant locally is not a norm. that is equivalent. So whatever you prefer, either the determinant in the sense like here, a number in K star, or the places where it's not the norm, whatever you prefer. Now, the first question you might ask is, well, if the rank, the signatures, and the determinants actually completely describe the isometry classes of such a space, okay, if I give you a set of invariants, can you come up with a space having these invariants? And this turns out to be actually quite easy. So if you give me a rank, a determinant, and the signatures at the real places, sigma I up to sigma R, all you have to do is, well, first of all, by Gram-Schmidt, I know that there must be a diagonal matrix which realizes that space. So the Gram matrix of that Hermitian space must be realizable as a diagonal matrix. And then you just have to make sure that the entries on the diagonal at the ith real place has the correct sign. Yeah. So I just, if you give me, say, the signature, you want ni to be the number of negative entries at the place I. Well, okay, I make sure that the first ni elements have signature -1 at the ith entry. I do that for all I, and then whatever such an element will exist. So for all possible sign choices, there exists an element. So I fill up the first m-1 entries just to make sure that the signs will match up. So it has the correct number of negative entries in the beginning. And then the last entry, well, I just fill it up with d divided whatever I've picked in the first m-1 places. Then obviously I have written down an m by n matrix. So the rank of my space will be m. It has the correct number of negative entries at the ith place. So it has the correct signatures. And the determinant obviously is d, and the product of the diagonal entries is d. And therefore this is a correct space. So finding such a space is not really hard. Now, we want to go to the arithmetic analogs of spaces. So from now on, set k and set e denote the ring of integers of k and e respectively. And inside an Hermitian space over E, I want to look at an lattice, or more precisely an set E lattice, and that is just a finitely generated set E submodule of V that contains a basis of V, or to put it a more precise notion, if you extend L by scalars with E, then you get back the whole space V. Now, once you give me such a lattice L, there's a second lattice, namely the so-called dual. And the dual is actually important for this principal polarizations. Yeah? So the polarizations for that, you need to know the dual. And the dual is defined as the set of all vectors in V that have an integral inner product with all the lattice vectors. And it turns out that this set actually is a lattice as well. And dualizing twice gives you back the original lattice, etc. So all these properties hold. For later, I just want to mention that maximal lattice is a lattice that has integral inner products with it. So all the lattice elements have integral inner products with themselves. And the lattice itself is maximal with that property. We'll need that notion in a minute, so I just want to mention that. Now, when we start with a lattice, we can have this dual lattice, and it might happen that the lattice and the dual lattice coincide, or maybe they might not coincide, but they might differ by some fractional ideal of E or set E. Yeah? And if this happens, so if L is A times L dual for some fraction ideal A, we call L to be an A modular lattice. The modular lattices, they turn out to be the building blocks of the lattices. I'll explain that later. But so these modular ones are in some sense the building blocks of the larger ones. Now, given any two lattices in, say, two different isometric, into different Hermitian spaces are said to be isometric if you can find an isometry from one Hermitian space to the other. Okay. That maps the first lattice to the second lattice. And the automorphism group of L are all the isometries from L to itself. And now again, just as before, for any finite place of K, you can extend the lattice L by scalars. So you tensor it with set the ring of integers of the completion at P, and you get the completion of L at P. And whatever I've defined here will work for LP as well. So you can also define a dual at the completion. You can say locally maximal. You get a notion of modularity, isometries, etc., etc. So this carries over. Okay, so now it's time for an example. The easiest example I could come up with is K equals the field of rationals. E is Q adjoint I, so quadratic extension. And L and L prime are the set I lattices with Gray matrices of 3 of rank 2, with Gray matrices 1, 0, 0, 5, and 2i minus i3. Now, believe me, the Hermitian spaces of L and L prime are isometric, and the two lattices actually isometric at all primes. This can be decided by checking local invariants. I'll explain that in a second. So just believe me that I didn't make any boo-boo here. So the lattices are locally isometric everywhere. But it turns out there can't be a global isometry from L to L prime. The reason being, the first lattice here represents 1. Yeah, the first basis vector has inner product 1 with itself. And there's no such vector on the right-hand side. So every lattice vector here, you will never find a vector of length 1. And therefore, there can't be an isometry, a global isometry, but there is a global isometry locally everywhere. So the local global principle doesn't hold for Hermitian lattices anymore. So, and therefore, one introduces what it's called the genus. So, given a lattice in a Hermitian space, we say the class, or more precisely the isometry class, is the set of all lattices in the same vector space that are isometric to L. And the genus of L are all the lattices that are locally isometric to L. Because without loss of generality, I can assume that all my lattices they reside in the same Hermitian space, so I don't have to check the infinite places anymore, simply because for the spaces, the Hasse principle holds, and therefore, without loss of generality, it suffices to discuss only lattices inside the same vector space. So we get the class and the genus. So in this example here, the classes are not the same, but the genus is the same. It turns actually out the genus consists of these two isometry classes. So in this example, you get two classes. And that's a general result. The result is much older than the one that I cited. It's actually a much more general result on algebraic groups. And in this, for Hermitian lattices, it says that the genus decomposes into finitely many isometry classes. I mean, it's clear that it decomposes, but the important part here is finitely. So there must be lattices L1 up to LH, say, such that the classes of L1 and classes L2, etc. If you unify them, you get the genus completely. And the number of classes that you need to exhaust the genus is called the class number of the lattice L, or more precisely of the genus. So in the previous example, the genus here consists of two isometry classes, and these are precisely the one representatives for these two classes. So just like in this ideal class monoid, the genus more or less explains or describes how far my lattice is away from having the local global principle. So it's a measure for how far we are away from having a local global principle. That's exactly the same idea. Yeah.
I'm sorry to interrupt. There's a question in the chat.
Sorry, I don't see the chat. Okay.
Of course, I will read it. Don't worry.
No. Yeah. Okay. Oh, if you want to read it, I'm sure.
I'm here to help. Yeah, up to you. So the question was about the plus in the union. Could you?
Oh, a disjoint union. It's a disjoint union. So it's really a decomposition.
Okay.
Yeah. So disjoint union. Yeah.
Thank you.
So again, it's just like if you want to look at the class group for a group that the ideal class monoid, you want to measure by how far you're away from having a local global principle. So now, once you know that the genus decomposes into finitely many isometric classes, of course, this immediately yields a few algorithmic problems. First of all, in a few seconds, I'll show you that the genus can be described by invariants, local invariants. So first problem would be, if you're given a set of these local invariants, well, how do you find a first starting point? How do you find the lattice in the genus if it's given by invariants? And now the second problem would be, if I give you two lattices in the same space, say, are they isometric or not? So you want to decide isometry. And last but not least, if I give you a lattice or a genus, whatever, you take the genus of the lattice and you want to decompose it into the isometric classes, i.e. you want me to find L1, L2, L3 up to LH such that this decomposition holds. Yeah? So that, of course, is the most important one. And that's also the most important one for the application where we want to describe the abelian varieties. Yeah? So we need the representatives of the isometric classes. I said previously when in this motivational slide, the first slide, that we need the description of all the isometry classes of unimodular lattices. Now it turns out that the unimodular lattices, they do not form a genus, but they actually form a union of some 2 power of genera. So they consist of 2 genera, or 4, 8, 16, whatever genera. So if you can solve these 3 problems, then you can solve the question at hand from the first slide, which asked for the number of isometry classes, or the isometry classes of unimodular lattices, at least for the maximal order case. So if the endomorphism rings the maximal order, then you could actually solve the problem, because there are finitely many genera consisting of unimodular lattices. And now, if you can decompose them, you're done. Okay. Now, before we continue with solving these 3 problems, of course, I want to say a few words about how to represent a lattice in a computer. And the idea is that you use a pseudo-basis. So the lattice L, it must admit a decomposition of the form AI xi, where the AIs are fraction ideals of E, and the xi's they form a basis of V. So M basis vectors x1 up to xm of V, and the fraction ideals A1 up to AM. And once you have such a pseudo basis, you can form all kind of basic operations, like you can compare lattice, you can add them, you can intersect them, etc., etc. You can take duals and so on. And the way I want to view these, or I view pseudo-bases well, actually, it's a handy global way of describing the lattice locally at all places. Because if you now come up with any prime ideal, any maximum ideal of E, of set E, then you know a basis of L localized at P. Because, well, all you have to do is from AI, well, you fix a uniformizer at P, and then you take the valuation of AI at P, and then pi to this valuation times xi, and so on. this will be a basis of L localized at P. So a pseudo-basis is more or less a global way of carrying around a basis locally everywhere. And this allows you to do certain kind of local manipulations. I want to give an example, what I mean with local manipulations. Suppose you are given any lattice in any space, so over E, say. And I want to compute the maximal sublattice that contain P times L. That is precisely, you want me to write down all the Lxi which have index P in L. Now that's the same thing as writing this down. So you want to write down the maximal submodules whose index is this prime ideal P. And this can be now done easily as follows. First of all, let M be the lattice given with this free basis here. So we take the free lattice with this basis. Now M is free, so M times P times M, well, that's a vector space over the finite field Z E mod P. Well, it's a vector space. So in a vector space, I know how the submodules with codimension 1 look like. I can write down all the subspaces of codimension 1. Say, yeah, then I take the pre-image in M. So this yields me Y1 up to YR. These are lattices in M having index P. And then the funny thing is, you can now define this one. You take Yi, you add P times L, and you intersect with L. And the harness works. So now, what this looks like, here's L, there's Yi, and here's P times L. Now, if you look at this picture and you take the completion at any prime ideal which is different from P, then LP and P times LP, so if you complete this at Q, then LQ and P times LQ, they coincide. So at any place different from P, I didn't change the lattice at all. It must coincide with L because, well, these two ones here coincide with L locally. And at the place P, well, at the place P, M and L, they coincide at P. And at P, I went down by, well, codimension 1. So this Xi here is the correct choice. This will work. Yeah? It has index P. And these are all possible choices. So this way you can actually descend or ascend or go down and change the lattice locally at a single place. And then, of course, if you can do it at one place, you can do it at a finite number of places simultaneously by the Genus remainder theorem. So that's the main idea of these pseudo bases. Yeah, you can make changes locally at a prime. Okay. Now, I said that locally, my Hermitian lattices are expressed by invariance. The genus is given by invariance. I want to make this a little bit more explicit. So suppose we are given any prime ideal of K. And I want to describe, well, the isometric class of the completion of L at P. And for that description, we actually have to find an ideal P of E, which sits above P times the small p and the ring of integers, and I want it to be fixed under the involution. Well, that tells you that the capital P is the small p, of course, times ZE, unless the small p is ramified, in which case it's the maximal ideal sitting above it. Yeah, so that's another way of saying. And now, once you fix the notion, the completion of L at P admits an orthogonal decomposition into smaller lattices, where each component is P to the SI modular for some ascending chains of numbers SI. And now the set of these SIs, they occur in this, they show up in this decomposition, together with the ranks of these modules and the determinants of these Hermitian lattices. They actually form a complete set of invariants that describe the isometric class locally completely. unless you're in some special weird case. Okay, let's not go there, but in almost all cases, this is a set of invariants that does the trick. And this is easy to work out. So now we come to the question that, well, you have given that as a genus by locally explaining to me how this decomposition looks like. Yeah? At almost all places, this will be only one integer. So in almost all places, this will be Sn S1 equals 0, and the determinant then will be the determinant of the same of the embedding space. So you actually only have to explain to me when it's not the obvious set of invariants. So those places quite differs from that. So now we are given these invariants, and we want to find a representative, a lattice having these local invariants. Now, first of all, from the local invariants, I do know the determinant of LP, because it's a determinant of all these factors here, and you multiply them together. So I know the determinant of this one here. Now, so the determinant of LP is fine. I know that. And once I know the determinant, then we've seen previously, I can construct a space that has a lattice with the correct invariants. So we start by constructing this space, this emission space that must support such a lattice. Now we start with any lattice in that space. I'm not very picky, I just pick any one. And then, well, you know that if you have two lattices over a Dedekind ring in the same space, then they must be equal almost everywhere. So in particular, I know that my lattice M must have the correct invariants almost everywhere. So suppose P is the set of all the places where I'm not correct yet. Then from this description of Jakobowitz with the previous result with these invariants and so on, you can immediately write down as a global lattice or a global module that locally at P has the correct isometric loss. Now we have a problem because now I have a global module that at a single place is correct, but this doesn't help me. This one doesn't live inside V. So what you can do is locally, I know that the embedding space here, locally, it must be isometric to VP. And now you lift that this isometry, this local isometry, you lift that to an E-linear map. And if you lift far enough that the image of XP locally at P, it will have the correct invariance. If not, then will you just lift a little bit higher, yeah? Make the approximation better. And then eventually the image of this lattice under that map, it will live inside V, of course, and it will have the correct invariance. And once you're there, and you've done that for all the places in P, then you're done, because now you take the lattice M, and then locally at all the places in P, you change it locally at P to be that image here. And I told you previously that using pseudobases, you can manipulate a lattice at a single place. Yeah? So you just start with M, and locally at all the places in P, you make sure that it looks like that. Yeah? It is this lattice locally here, and equal to M on all the other places. And once you do that, well, yeah, we are correct at those places not in P, and at the places in P, we are also correct because by construction of this isometry of this lift. So then by the end of the day, we have a lattice that locally is correct. It does lie in G. Now, for the second problem, the question is, how do we compute isometries of lattices? And I don't want to go through the details, but the idea is the following. Let's just forget that we're talking about Hermitian lattices. So suppose we are now talking about positive definite bilinear spaces over the rationals, just like in linear algebra. And we have L and L prime set lattices, so that's just 3 set modules. And the set of all vectors inside such a lattice of a given length b, or at most b, that is finite, and it can be enumerated by the Finke-Post algorithm. So there's a method of computing that, and it's implemented in Magma Sage, etc. So you can ask in a definite lattice over the integers, you can ask for all the vectors up to length 10, and then it will readily give you that set. And now the idea is, if you want to find an isometry between two of these positive definite bilinear spaces of the rationals that map one lattice to the other, the idea is, well, if you make this set of vectors or up to length b large enough, eventually this set will generate your lattice, or at least it will generate v, which means that any bilinear, any linear map from L to L prime will be uniquely determined by the image of such a finite set. So what you have to do, if you have to guess the image of the vector b1, the image of b2 up to bm. And of course, the image of b1 must have the same length. So if b1 is a vector of length that knows capital B, then the image also must be of that length. So what you do now is, by backtracking, suppose the first I-1 vectors, they have already been chosen, the first images of the first I-1 vectors have been chosen. Then you pick the ith vector such that it has the correct inner product with the images already chosen. And if you can't find such an image, well, then you go back and choose another image for this one here, because obviously this one was wrong. Yeah, and then you rinse and repeat. Eventually, by an exhaustive search, you will find an isometry, if it exists. Now, using a similar trick, you can find the isometries of L to L itself. That's the automorphism group of L. And I can not only find lattice isometries between two lattices that fix a form F, I can also add additional bilinear forms G and G prime, and they don't have to be positive definite anymore. Yeah, I only need positive definite to get a finite set here. So I can have additional forms, like G and G prime, and they will be preserved as well. The only thing that changes is here, I get here more conditions. But I mean, having more conditions is even better, because it limits the number of choices I have in each step. And now the result is, if we go back to our Hermitian lattices, in a positive definite Hermitian space, they are isometric using, they can be checked for isometry using the previous trick, because for any number in K, I can define a positive, or I can define a bilinear form over the rationals by looking at V as a rational vector space, and I define the form to be, well, you map x, y to the inner product x and y with your Hermitian form, you multiply by A, and then you take the trace. And that is a bilinear form over the rationals. And it turns out that a set linear map from L to L prime is an isometry of Hermitian lattices, if and only if it's an isometry of set lattices, and it maps it preserves F1 and F1 prime, and it preserves FA and FA prime, where A is a generator for K over Q. Yeah, so by the trick, we can compute an isometry satisfying mapping from L to L prime, and it maps the inner products with respect to F1 to inner products of F1 prime and FA to FA prime. And then this will be automatically in Hermitian isometry. So for the last few slides, I just want to explain how to decompose the genus.
So you have 5 minutes officially.
Okay, so let's explain how to decompose the genus into isometry classes. Well, the problem is the unitary group doesn't have strong approximation, and that's why this is a little bit tricky. But the special unitary group, so if you intersect the unitary group with the SL, then you do have strong approximation. And the idea now is instead of looking at the genus, you have the genus, and the genus decomposes into isometric classes, and then there's something in between, which is called the special genus. So two lattices are said to be in the special genus if you find an isometry phi such that L prime, phi of L prime, localized at P, is locally isometric to LP, where this local isometry has determinant 1. And this actually defines an equivalence relation which is finer than being the same genus, but coarser than being isometric. So this tells us that the genus decomposes into finitely many special genera, and each special genus decomposes into finitely many isometric classes. So we go down, we do this decomposition here of the genus into isometric class by 2 steps. I explain first how to decompose into special genera, and then we decompose the special genera into isometric classes. Now, for this first step, we need to know what a neighbor is. If P is a prime ideal, we say that a lattice L prime in V is a P neighbor of L. If the intersection of L and L prime is has index P in L, and it has index P bar in L prime. And then there is a result by Shimura, which says there exists a computable set of prime ideals P1 up to PR, such that if you fix any PI neighbor of L, and you call that Li, then the genus decomposes in the special genera of the Lis. And this set is computable. And I worked out how to do that. So this decomposition here is easy because it follows from local computations. You need to compute some Ray class group, some quotient of a Ray class group. Yeah. And which quotient to pick, that depends on the genus, of course. But this is some easy to do computation. You get the set of primes, you fix a single neighbor, and then this will give this decomposition. So last slide for today. The last thing that we're left with is how to decompose the special genus into isometric classes. Well, first of all, if your space is indefinite, so it's not definite, then you're done, because strong approximation tells you that the special genus, they consist of a single class. So there's nothing to do here. And in the definite case, well, it's more involved. But there's a result or method due to Kneser, which gives us a method to do that. And the idea is this result of Shimura tells you if there is a prime such that taking the prime P such that taking P neighbors of L, do not change the special genus, because it's a quotient of a Ray class group, and if you're trivial in that quotient, then this prime ideal will not change special genera. So suppose I have such a prime ideal. Then we define on the isometric classes in the special genus of L, we turn that into a graph. We say that the class of M is connected to the class of M prime if M prime is a P neighbor of M. And this defines a directed graph on the special genus, and it turns out that graph is connected. So in other words, decomposing the special genus into isometric classes is nothing but to ask for a spanning tree. And of course, I mean, you know how to find the spanning tree. You start by the lattice L, you compute the neighbors, you check them for that they are not isometric. And then you start by computing the P neighbors, and you make sure that you don't get any duplicates, and so on. You go on, and eventually you exhaust the whole graph, and then you're done. And now if you combine the two results, then this tells you how to decompose the genus into classes. By doing it in 2 steps. First, you decompose it into special genera. This is done locally by local invariance. And then for each special genus, you use this graph procedure by finding spanning trees to decompose it into isometry classes. Now, one last remark. On this motivational slide, I I had R lattices where R is an order. It's the endomorphism ring of your elliptic curve. This might not be the maximal order. And if it's not the maximal order, then the result becomes a little bit more tricky. But what you can do is, if you have an order which is not the maximal one, you compute the unimodular lattice of the maximal order, and then you go down. So by computing now the unimodular lattices of the orders having a certain index of prime. And then you go down by another prime, another prime, another prime, until you hit your order R. So you can actually go down, at least for projective modules. That's fairly easy. So that's why I was cheating a little bit, because later on I was only discussing the maximal orders, but the other orders can be solved along the same lines by first solving the problems for the maximal orders and then descending down. That was all I wanted to say.
Thank you very much, Markus. We may unmute now and clap. Maybe you can stop sharing your screen, or just sharing again your slides.
Okay, yeah, I can.
Up to you.
I can, whatever you want me to share.
Okay. So are there any questions or remarks for Markus? So I do have one to launch
Okay.
the question session. So in the case where the lattices come from the elliptic curve case, the motivational case we want, can you say something about the little r and little t that appeared in your talk? The number of elements in the decomposition that you had. You decompose the genus into special genuses and then into classes.
Yeah.
You have an r and a t there.
Oh, okay. It will work. Say it will work quickly if t is less than 100. The r is not important. The r is it doesn't matter how large the r is. The t shouldn't be. If say it's 100, then it will work in a couple of minutes. If it's say 1,000, it will take a day or two. So that is the largest I would say is feasible. Yeah. The number of special genera, it's not important, because it's explained by local invariants, and you only have to find a single neighbor. So this decomposition here is done quickly, in less than a minute or so. But here, I mean, finding the spanning tree here is a search. It's like a big bucket, and you have t elements in that bucket, and you pick one element by random, and you look whether it's new or not, and if not, you throw it back. And they are not equally distributed. The number of automorphism groups, it decides how likely it is that you pick the element. And if it's reciprocal, it's the probability is 1 over the number of automorphisms. And in general, there are 1 or 2 of these lattices with huge automorphism groups, which makes them more or less impossible to find. That's why t equals 100 is something that is doable, and then it will just be more or less impossible.
Thank you. So let me see. I have some. So Björn Poonen, you had a question?
Yes. Well, yes. I was just wondering if people have studied algorithms for indefinite, for lattices in indefinite Hermitian spaces.
More or less the only difficult thing is finding an isometry. Finding the isometry is a problem, because the decomposition of the genera is doable. And it's also doable to actually say in which special genera you are. And because in an indefinite case, the special genera are the classes. So I can tell you if you give me a lattice in which isometry class it falls. So I can tell whether two lattices are isometric, but I can't find the isometry.
Okay.
So that is the problem. Some invariants will tell you whether they are isometric, but finding the isometry is the problem. That's the only problem.
In principle, I suppose it's doable, but maybe the bounds are horrible.
Yes, yes, that's right. Of course. I mean, if there's an isometry, it must have a bounded height in the entries. By an exhaustive search, you'll find it eventually, but yeah, but it's not feasible in practice.
Okay, thank you.
Thank you. So Andrew Sutherland.
Yeah, this might be a naive question, or maybe one for your co-authors, but I was curious if there is a geometric connection on the abelian variety side with the special genre that you talked about. You're decomposing these genus into special genre and then finding the isometry classes within them. Within them, what does that mean on the other side of the functor?
Okay, Christoph.
Actually, I don't know either. And it's the same a bit what he explained with the neighborhood method and all this. I would really like, someone to tell me a bit how it looks like on the other side. And for instance, as Markus said, we have a graph, and well, cryptographers become nuts now when you speak about graphs. So I'm really wondering if this neighborhood steps where you go with isogenies, it looks like isogenies of a given degree. If this mimics perfectly the situation, what happens on the other side. But when we thought about it, writing the article, we were not really able to say if it is somehow related or not. So yeah, it would be really nice if someone can jump in and tell.
Yeah, thank you.
Would be nice to have a description here.
Christoph Ritzenthaler, you had a question?
Yes, I was just, it was more like a comment. Markus, I think that you have also some algorithm for quaternionic lattices, right? That where you can...
yeah, okay. I didn't go there, but okay. Originally, my idea was not to do something about abelian varieties because I'm more doing number theory. So my idea was to classify all the one-class genera of lattices in definite Hermitian spaces. And this actually also works for the case where E equals K, so we have quadratic forms. Then bar is the identity. And in the quaternionic Hermitian case, the E is a quaternion algebra and bar is the canonical involution. So, and in all these cases, I have these algorithms and I can work out the genera and etc. And actually, I worked out the one-class genera.
Because even if you were not thinking about it, it can still be used for, enumerating abelian varieties. The functors still work for certain cases, the singular ones. So, it could be really used if people want to try to extend also the method for other types. Thanks for the answer.
Thank you. So there's a question in the chat. Everett, do you want to intervene or you want me to read it?
Oh, yeah, if you read it, that's easy.
Yeah, well, mostly it's just, I was wondering, there's a recent paper of Brock and Jordan where they were talking about isogenies between abelian varieties, and it turned out, they found out afterwards that some of the results were already known in different language. And I think the different language might have been a neighbor method type language, but I don't quite remember this exactly. So I'm just thinking that might be a place to look for a connection between those two ideas.
Okay.
Thank you. Thank you. So if there's no other comments or questions, I think it's a good time to thank Markus again. You can unmute. That's the end of the second part of the day, and the third part will start in an hour and 5 minutes at 10 p.m. Paris time. So have a good dinner if it's dinner time, good breakfast if it's breakfast time, a good break in any case, and then I give back the word to the organizers.